Homework 12, page 169, 36, numbers 1, 3, 5, 9, 15, 19, 21, 25, 27, 29, 31, and 41. I think that's 12 problems. After 3.6, we are going to skip 3.7, not because the stuff in 3.7 isn't good, it's just not really necessary, and I'd like to cover other stuff. So you can check out 3.7 if you want. That's called Rates of Change in the Natural and Social Sciences. Obviously, I don't care. No, I'm joking. It's actually really cool stuff. In fact, there's some really, that leads to some really cool stuff. Victor, I think you know the logistic map. You remember this, right? Like, and that has to do with growth of population and stuff like that. Really cool stuff. Just, I'd rather move on to other stuff. So we're going to move from, on Thursday, we're going to do related rates, which is section 3.8, which is a must if you're taking calculus. Because we're actually going to start to get into some applications of all this stuff. Noah, you're leaving.
Yeah, I won't be here on Thursday.
Right.
And then I might be here on Tuesday.
Okay.
It's just, I think I probably won't be because
Okay.
it's a 6-hour drive.
Yeah. So, at any rate, what I'm just going to, I'll try to have these posted as soon as possible. And should that give you enough time if they're posted later in the day to do whatever?
Yeah.
I mean, I'd like to not have to like email you and say here's the assignment and stuff like that. Like, I think if I just post it online,
Yeah.
it's one of the reasons I say this every time. In case you guys wrote something down wrong or whatever at the beginning, I always say the things just in case in the video, if you can't see it very well, you have also me saying 1, 3, 5, 9. So, kind of, yeah. Okay, so we should be good. We won't be having any pop quizzes or anything like that, so you'll be fine. All right, let's start with our topic for today, which I'm not going to tell you what it is. I'm going to leave that out there, and I'll eventually tell you when we get to page 2 of my notes. First off, what's this?
Circle.
What circle? The unit circle, right? It has radius 1. And it's centered at the origin, right? It is the unit circle. Okay, so I have a couple of questions about the unit circle here. So first off, we know it goes through here at 1, goes up to 1, then so on and so forth. Is this a function? No. Not as written.
It's 2. It's a vertical line.
Right, yeah, exactly right. It fails the vertical line test. You plug in 1 input here and you get 2 outputs, by definition, not a function. But, can we turn it into a function?
Yeah, I would be like,
How do we do that?
y equals 1 minus the square root of x.
Okay, one step at a time there, Turbo. What do I need to do? So, in other words, you're describing how you would do what? To
solve for y.
Solve for y, right? Or, yeah, get y in terms of x, solve for y, get y by itself, right? That's what you would do. And so, now you tell me step by step, Turbo, how we're gonna...
So minus the x squared.
Minus the x squared. So I got a y squared, 1 minus x squared over here. Then what do I do?
Square root of both sides.
Take the square root, and when I do that, what happens?
Plus or minus.
You get a plus and a minus. And that is what happens here. Now, in other words, now we break this object gets broken into 2 functions, right? We have the top branch of this function, which does something like this. That would be where y is the positive 1 minus x squared. And then we have the negative branch of this function, where it does this. And you could find all of those. So you plug in any given value of x, you want to know where do you go in y? Well, that's given by y equals negative 1 minus square root 1 minus x squared. Right there. Everybody with me?
Yeah.
Okay? So, this is just, quick review. But let's say we wanted to find the derivative at a given place on a circle. Let's say we wanted to find the derivative right here. And let's say that point is at, I don't know, square root 3 over 2, comma 1 over 2. You could check that is indeed on the unit circle. If you plug those into there, you do get a 1, right? You can also see that by plugging in the x into here, and seeing, or into here, and seeing that, yeah, you'll have a 1 minus 3 over 4. That's 1/4. Square root of 1/4 is a half. Right, that kind of thing. Okay, so I want to motivate this, with an actual question. Let's suppose that we're trying to find the equation of the tangent line at this point. There's that point right there. What do I need to do?
So take the derivative
Of
y. Probably y equals the square root of 1 minus x squared.
this guy? The
Or-
top branch, right? Because
the
the point's on the top branch, right? So you have to kind of use your brain, and so you can't just, that's the thing about this type of setup. Once you've broken an object into 2 bits, or multiple bits, because what if your object looked something like this, right? Then, yikes, we could be breaking it into all kinds of different things, and it depends. But in this case, it's pretty simple. You have 2 choices here. Obviously, if this is in the first quadrant, you want the function that gives you the thing in the first quadrant, right? And so, what you're telling me then is if I wanted to find the slope, or yes, that's what we want to do. But let's motivate this by, we want the tangent line right there. Well, we're going to need the slope right there. So we need the derivative right there. So we need a function, right?
Yeah.
We need to get, and we'll just forget about this plus or minus thing right now. We'll say, what you need is y as a function of x. Okay? Right? So let's do that. So now we have y as a function of x. What do we need to do to it?
Take the derivative.
Take the derivative. So we want y prime. And what is that?
1 over
1 over, yeah.
2
2.
times the
Times root
times
1 minus x
yeah.
squared times 2x.
Times what?
2x.
Are you sure it's 2x? What's the
Negative
derivative of this
No,
function?
it is.
Yeah, careful with that. That'll always mess you up, right? It's negative 2x. So the 2's cancel, and I get y prime of x is equal to negative x over 1 minus x squared. So there's the derivative. Now, I want to put this up somewhere. Let's get this somewhere where we're not going to forget it, because we're going to want this guy later. I said that y prime is equal to negative x over root 1 minus x squared. Okay. All right. Now, why don't we go ahead and find the actual equation of the tangent line? So, first off, we want the equation of a tangent line. What form does it have?
y equals x equals.
Okay. So we need to find an m and we need to find a b. And so, how do we find the m?
Plug in root 3 over 2
Plug it into where? Into here?
into the derivative function.
Yes, because the derivative will tell me the slope. So what you're telling me is that the slope at this point right here, where the x value is root 3 over 2, the way to get that is I plug in root 3 over 2 into this function right here.
Yeah.
Okay, give me just a second. We also found what? That y was root 1 minus x squared. Okay, I'm going to have that up there for a second. You'll see why in a minute. All right, so I plug that in, and I get negative root 3 over 2 over the square root of 1 minus root 3 over 2 quantity squared. So that gives me negative root 3 over 2 over, let's see, that would be 1 minus 3/4, right? When I square root 3 over 2, I get 3/4. 1 minus, that would be 1/4. And then the square root of that is 1/2. So that's the square root of 1/4, which is, I'll just rewrite it here, 1/2.
And then it's like just negative root 3.
And yeah, and so what I'm seeing here, I'm going to do this again, right? I'm dividing by a fraction. That's the same thing as multiplying by its reciprocal. So multiply by 2 over 1. The 2's cancel. And we get that the slope at this point is equal to negative root 3. Notice I had to plug something in. I'm I'm not plugging this formula in for m because that's not going to help me. That's not going to give me a line. I got to get an actual number out. I got the actual number, so I'm going to take this, plug it into here, replace it here. I get y equals negative root 3x. That root 3 is my m plus, or the negative root 3 is my m. Now what do I do? What do I need to do?
So
An x and a y.
yeah.
Okay.
Solve for b.
So plug in the root 3 over 2.
Plug in the root 3 over 2 for which?
For y.
For
X.
For yeah, there you go. Negative root 3 times root 3 over 2, there's your x, plus b gives you what as an output? It had better, right? Because that's the whole idea here. We want the line to have the same output as the circle. And so when I plug in a root 3 over 2 into the circle, I get out a 1/2. When I do it here, I better get the same thing, so I get a half. That root 3 times that root 3 is the same thing as negative 3 to b 1/2. So b is equal to 1/2 plus 3/2, which is 4/2, which is 2. Okay? So I'm going to go ahead and write that right here. Y is equal to negative root 3x plus 2. So, okay, we did the thing that we set out to do. Okay, that's cool. Now, we had something that wasn't really a function, right? And for whatever reason, whatever's motivating us, we needed to find the derivative of it. Now, maybe, I mean, here we needed it at a point, but maybe we want it more generally or whatever. For whatever reason, we need a derivative of the thing. Now, in order to do that, we needed to solve. We needed to get one of the variables by itself. Now, it also would have worked if we would have got x as a function of y. It would have been a little bit different, but instead of plugging in x's, we would have been plugging in the y's and etc. But that's neither here nor there. It's here. It's something to keep in mind with this section because usually we'll want to get y by itself, but you might have a problem that says get x as a function of y, and that's perfectly good, right? Okay, so what did we have to do? We got our thing. We had to get one of the variables by itself, right? We isolated the y to get y as a function of x. And so then y is then, you could consider it to be a function, right? Y of x. But what if, so I'm going to get rid of all this stuff here. What if the thing that we're trying to do something with isn't this simple? What if it were something like this? 1 plus xy equals sine xy squared. How in the world would you get one of those variables by itself?
Well, minus. Oh, yeah. Yeah, that's
Good luck! I mean, and yeah, and you see, when I originally did this one, I copied this right out of the book, and it was just 1 plus x, like that, and you could take arcsine of both sides, and that's fine, but if you tried arcsine, you still have now your x's and your y's are still locked up. Now what do? I took this and plugged it into Wolfram Alpha, and it had no idea what to do.
Oh.
So there are some functions which you cannot isolate one of the variables. You cannot write it one as a function of the other.
Yeah.
So, like, the thing that you're working on, in this case it was easy. In fact, it was one of the easiest ones that I could think of to get one in terms of the other. But very often you don't have that option. It's either impossible or ridiculously hard to get one of the variables in terms of the other. And so that's our topic today. It's called implicit differentiation. Differentiation. I'm going to abbreviate that. Implicit. Now, what we did here is we took a object. This thing is not a function. It's an object, right? and we turned it into an explicit function, right? We found y as a function of x. And of course that kind of split the thing up, and we can't consider the entire thing in and of itself. We took a branch of it and yada blah 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 blah. But the thing was, we were able to get an explicit expression here. You can't always do that. So the thing is, as this is written right here, so here's the explicit form of this part of this object. But implicitly here, the implicit assumption is that this thing, whatever it is itself a function of x. You're assuming that y is a function of x. Does that make sense what I'm saying here?
Yeah.
Like, it might be, and like forget about the circle for right now. Let's say we had some kind of relation like this. Plus, I don't know, 2x cubed plus x squared equals, I don't know, 5. Something like that. Here, we have some kind of relationship, blah, 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 blah. But this itself, right, we're saying, like, if you just saw this, you'd say, yeah, we could treat this as a function of x. Like, in fact, just forget about this part for right now. Forget about the equation thing. If I said, is that a function? You'd say, yeah, it's a function of x. You plug in an x, it will give you some kind of output, right? But the idea is here, and that's kind of what's going on here, right? We didn't know ahead of time that y was actually equal to the square root of 1 minus x squared. We're just saying, maybe y is a function. We may not know the explicit formula here, and that's kind of what we're doing with. This is a way of thinking about this relation that I have up here. It's saying, we're going to pretend for a second that this y does have a formula. We may not know what it is, but we're just going to say, okay, y is some kind of function of x. And that's what we mean by implicit here. That one of these things, and we could have done it the other way around too. We could have said x is a function of y. But what we're going to pretend now is that we have something like this. And we're just going to say, you know what, I may not know the exact formula for what y is, but I'm going to pretend that there is such a formula. And so, in other words, this is implicitly a function. Everybody get the lingo that I'm using here?
Yeah.
Any questions on that before we go? No? Okay. Okay, so now let's say that now, instead of forget about this guy and forget about all the stuff in red here, let's say we want the same thing here. We don't know what y is, but we know that we need a y prime for whatever reason. Maybe we're trying to find the tangent line or whatever. But for whatever reason, we need the derivative of y. That is, we need y prime of x. Watch what happens when I take this equation and I take the derivative of both sides. We're going to say, okay, this thing's a function of x. So, or seeing that like that, right? You could say, there's some g of x, and it's x squared plus whatever the heck y of x is. Maybe there's a cool formula for it, right? Maybe it's 2x cubed plus x or whatever. Who cares? We don't care right now. In fact, we're going to make life easier by just writing it as y, and we have that. Now I'm going to say, let's take the derivative of that. Okay? Everybody with me?
Yep.
Okay? And just watch what happens when I do this. I'm going to change colors because my blue is starting to fade. So I'm just going to take the derivative of this thing. And whatever I do to one side of the equation, I got to do it to the other side of the equation. So I'll just take the derivative of both sides. Let's get the easy one out of the way first. What's the right-hand side?
0.
0, thank you. Okay. 0. Okay, now let's take the derivative of this. We have some function, don't know what it is, and I'm squaring it. Now, so I can take the derivative of this part and add it to the derivative of this part. What's the derivative of that?
2x.
2x. What's that?
2 times y of x.
2 times
y of x times the derivative of y of x.
times the derivative y prime of x, right? Chain rule!
Yeah.
You see why we're learning this after we do the chain rule, right? It's like, okay, well now, wait a minute. What did I say I needed? Y prime of x? There's y prime of x. Can I get it by itself?
Yeah. Minus the 2x.
Yeah, so I'm gonna, okay, so I'm gonna get rid of these parentheses for a second. I subtract this off and I get this. Now what do?
Divide by
by
2.
To get the
Y.
2's
Okay.
and get the y out of there, right? So I bring the y downstairs and I get negative x over y of x. And you say, that's not that. Where is it? What's y of x? Oh, well, look at that. Y is that thing. It's the same. Look at that. Ha! That's interesting. The only problem is, and I've kind of cheated here a little bit, is you'll notice that as I've written this, this is actually a y. It's not really itself a function of x. It's just whatever the y value is. So this thing isn't purely a function of just x. It's a function of x and of y. So if I wanted to be really proper here, I should say y prime is a function of both x and y. But what I'm about to do is drop this of x nonsense right now. So what this would look, I'm going to go through this one more time, this little part here, and show you how you're going to deal with this. Like in your head, whenever you see a y, you're going to think that itself is a function of x. I'm just going to stop writing the of x part right here. Is everybody okay with that? Can I do that? Because whenever you see something like this now, we have to choose, okay, one thing's a function of the other thing. Let's let y be the thing that's the implicit function. And we're just going to stop with the parentheses. We're just going to do this. So I have some relationship. I want y prime. And so I take the derivative with respect to x, treating y as a function of x. And so the 2 comes down here, the 2 comes down, up times y prime, right? Chain rule, because y itself is a function, gives me 0. We do some solving, we get y prime by itself by getting that guy over there, and there you go. Now let's finish this up. I want to reproduce this here. So I want a y equals mx plus b, right? Let's do it in green. We have a black y already. Let's do it in green. We want a y equals mx plus b. How do I find m? How do I find the slope right here at this point? Given this.
For negative, for root 3 over 2,
Yep.
plug it in, so it would be y prime of
So
root
y
3 over 2.
okay is negative root 3 over 2 for x. What do I plug in for y?
We need to.
Oh,
We can just
a
make
1/2, right?
There's your y value. It's right there.
Yeah.
That's pretty cool. And now, if it were possible, it happens to be possible that you can solve this thing. And you could, if you wanted to, plug it, okay, y equals 1 minus x squared. And so when I plugging in the root 3 over 2 into here, I get 1 minus root 3 over 2 squared, which indeed is root 1/4, which yes, gives me 1/2. Or, we know the point. Why make your life any harder than it needs to be? It's given, right? And so you get this. You get negative root 3 over 2 times 2 over 1, which gives you negative root 3, which is what we got there. Blah, 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 blah. Plug it in and you'll find the 2, etc. Right? You get the exact same thing. I don't know about you. I think this is pretty cool. What's really nice about this is if you're given some kind of crazy object and you want to find and a point on it, you don't need to go through all of this to get this guy and blah, 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 blah. This turns out to be much easier, right? Like, think about what we had to do to get to here. We had to first get to here. We had to solve for y. Then we had to take the derivative of y to get that. Here, we just started with the thing, took the derivative, and boom, there it popped out. Way easier. And in a case where it's impossible, which is what we're about to do, like there's no way to solve. If there's no way to solve for y, you couldn't get a derivative by going this route, right?
Yeah.
So, any questions on this before we move on? Are you sure? Do you buy this? Another cool thing about this is we didn't have to break this thing into branches. And you'll notice, here's something to notice. The slope should be negative anytime you're here in the first quadrant, right?
Yeah.
And when you're in the first quadrant, both your x value and your y value are positive, right? And so plug in a positive and a positive, and then make it negative, and you get a negative value.
Wow. Yeah.
Down here, in the fourth quadrant, your slope should be what? Positive or negative? Positive. You have a positive y value, positive x value, negative y value, positive over negative, then make it negative, and it's positive. You could do that with all the other quadrants, etc., right? And it works for the entire circle. So that's one of the cool things about this. On the other hand, you don't have it as a function of x, which limits you in some cases. Like, if you didn't know what this part was, you might have a hard time finding out what the y value is. But
Couldn't you just plug it into the original?
you could plug it into the original equation, and then hopefully things get nice. But good luck if it's something like what I'm about to write on the board. So it has its uses where it's useful. Sometimes it's not always useful, right? So did I do that one? Yeah, so here's the one. Okay, so, yeah, we did that, that's good. So here's that one I wrote up earlier. xy equals sine of xy squared. And now we want the derivative y prime. So what am I going to do?
So
What do I need to do?
take the derivative of both
Take the
sides.
derivative of both sides of the equation. That's step one, right? So with respect to what?
Um,
Y or x?
y. Right. Oh wait. Oh.
We want y prime. So what we're imagining here, right? I'm not going to write this up, but as soon as we say that, we want y prime. So I'm going to imagine in my head, okay, everywhere that I see a y, it's actually some function of x.
Yeah.
Right? So like for instance, it's like 2x cubed plus 5x, right? And if that were up here, everywhere that we saw that, this would be 1 plus x times 2x cubed plus 5x. This would be sine x times 2x cubed plus 5x. And then we would go through and do all the stuff. But now we're just saying, let's make our lives a little bit simpler. Instead of writing all this stuff out, we'll just write it as a y. And whenever I take the derivative of it, I'll need to write y prime, right? Or possibly use the chain rule because this part's squared, right? Okay, so let's do it. We're pretending y is a function of x. And I'm taking the derivative with respect to
X.
x. So we're treating x as the variable. When I do that, what do I get over here?
2. Oh no, because you have to. So 1 plus or 0.
0, yep, the derivative of 1 is 0, so he's gone. Now what do I do here? X times y, the derivative.
So take the derivative of the first thing and then times
And what is the derivative of that first thing?
1.
1.
And
1 times y, okay, so 1 times y
then leave the
plus,
second. Yeah. Just x.
leave the first one alone,
So just x and then times 1.
times what?
1.
Y of x, what's the derivative of y of x?
Oh, y of x. Right. Then it's y of
Y prime. It's the thing we're looking for. And this is the beauty of this, right here. As you do this, the thing you're looking for should pop out, right? So for instance, if instead of y, if we said y of x is actually, let's just say it was actually sine x, then what would this be? 1 plus x times sine x, and I tell you take the derivative of it. Forget about all this stuff up here, and you tell me what do I need to do?
So it's, well, the first 1 is 0.
1 goes to 0.
And then so take the derivative of the first So 1 times sine of x plus cosine of x.
Plus, leave
X
that part
times
alone. X times cosine x. And so you'll notice here, that's exactly what this is, right? If the sine of x was a y, that's what's left over there, right? Same way that's left over there. And x times cosine, what's y prime? If sine is x?
Cosine of x.
So yeah, it's cosine, right? It's whatever that derivative happens to be. So right now, right, it's like it's hiding out. We don't know the explicit formula, but that's whatever its derivative is.
Yeah.
Right? It's like here we know the explicit formula, so we could actually do the calculations and end up with, yes, your y stays here, plus x times whatever that derivative of y is. Here we don't know what it is, but we're pretending, like, you could pretend that you have this information somewhere, and then you do the work here so that it's not all ugly, and then you could plug it in later or whatever. But this is the idea. This is the thing that you're looking for, is that y prime. Right? And so it hit better, because that's what we want. I even wrote it up there and boxed it, right? That's what we want. And so we better do something that makes that y prime pop out somehow. Okay, let's continue on. We're going to have to use chain rule, product rule, and chain rule again. Or, yeah, for this one. So what do I do with this?
So it's
We have
cosine
sine of a function. And so we take the derivative of sine of a function and we get
of cosine of x times y squared
xy squared times
times
the derivative of
Yeah.
whatever's in there, right? Xy squared. And so what is the derivative of x times y squared?
1 times 2y plus.
1 times 2. So wait a minute. We have a product.
Yes, you take the derivative,
Take the derivative of the first one,
which is 1.
which is 1, times y squared, right?
Oh yeah.
Yeah, you said 2y. You took the derivative of
Yeah.
both and
Yeah.
put them together. We want to take the derivative of the first one, leave the second one alone, right? So, okay, I'm going to expand this out 1 second. Okay, so I'm taking the derivative of this. The derivative of the first thing is
1.
so I'm not going to write it. Leave the second thing alone. Add that to, leave the first thing alone. Take the derivative of this. What do I get?
2y.
So it's
2y.
yes. Yeah.
Times
Um.
y prime. Remember? So if I wrote it like this,
'Cause it's,
maybe you might want to do this, because you guys are forgetting that y is not just a variable; it's a function. Okay. And so, like, for instance, if y of x, again, if y of x happened to be a sine x, and you had this right here, you tell me, what's the derivative? Let's do this. What's the derivative of this guy?
so 1 times sine of x
1 times sine x squared
plus
plus,
2x
leave that alone,
times 2 times sine of x times cosine of x.
Yeah, right? Because the chain rule, right? You keep taking derivatives, and we're pretending now that y is some unknown function of x. Maybe it happens to be sine x, I don't know. That might actually do, I won't, but we can pretend for a second it is, and look at what happens, right? Y squared is still there. X is still there. 2 is right there. Whatever y happened to be stays put. Because he was squared, the 2 drops down, it goes down to 1, he stays there. But then we have to multiply by the derivative of the inside stuff. We don't, in this case, we don't know what that y is. If you knew what the y was, you would just do it. Here, we don't know what it is, and so we have to bring that y prime out there. Otherwise, it ain't going to work, right? Because this is key to what we're doing. It's one of the, I like how the book did this right after we do chain rule, because now you're like used to doing this, right? But now we just have to see y as a function itself, and every time we take the derivative of it, we have to remember, oh, that it's not just a thing. So in this case, right? You say leave, we took the derivative of this. We said, and with respect to x, take derivative of the first thing, which goes to 1, leave the second thing alone. Leave the first thing alone, take the derivative of the second thing, and you have it in your head like, oh, the derivative of y is 1. Well, yeah, with respect to y, it's 1. But with respect to x, you're pretending that y is a function of x. And so, well, we just have a nifty way of writing that, and that's just y prime, whatever that derivative happens to be.
Yeah.
Everybody with me on this? I'm going to get rid of this homework, too. Okay, so, all right, x, y prime. Let me clean this up a little bit. We have y plus x, y prime equals. Now, I'm going to distribute him into here and put the y squared out front. Now, this stuff, that's going to be 2xy y prime. And I distribute the cosine in to give me a cosine xy squared. Now, it's on the board. What am I trying to do? What do I want?
Y prime.
I want y prime. So what do I need to do to get y prime?
Get all of the things with y prime in it on the same side.
Yeah, and get everything that doesn't have a y prime in it on the other side. Okay, so I'm going to choose to bring this guy over here, and this guy, take him over there. So I'm going to say y minus y squared cosine xy squared. Right, I just brought him over there. Bring this guy over here. I'm going to write the positive thing first. 2xy y prime cosine xy squared minus that thing, xy prime. Okay?
Now factor out.
Factor out a y prime, right? And so I'm going to do that. I'm going to pull this y prime out front. Everything over here stays the same. Y minus... Hey guys, could you keep it down, please? Thank you.
It hurt me.
I'm sorry, bud.
Let's purpose.
I'm sorry, but I will adjudicate this later. And so now, if I'm not going to go ahead and waste all my time writing that out, because what's going to be my next step? I'm just going to take that and divide it. So why don't I go ahead and just write it down here, right? So what's left over after I pull that out?
2xy
2xy
times cosine
2xy cosine xy squared
minus x.
minus and just an x left over. And there you go. Okay, so got that right there. And then if we said we wanted the derivative at 1, 2 or something like that, if that happened to be on there, I actually tried to find a point on that. It is not easy. I graphed that thing. It's wicked crazy looking. And so,
How do you... Well, that's no graph. If you...
it can do implicit graphs. You could just plug this in.
I thought you had to have it as a function of y.
Nope. Desmos knows how to deal with it. I think what it does is it takes your graphing, whatever, the field, and it just goes point by point and says, okay, this point is like -5, 2, and it plugs it in and says, are they equal? And if it is, then it does it. Or if it's really, really, really close to being equal, it'll put a point there. And then it moves to the next one and says, okay, is this point on there, and so on and so forth. And that's why it might look a little crazy, like it has little dots everywhere and stuff, and
Yeah.
it'll do that. But now, yeah, if you needed for whatever reason, this is some kind of curve, and you needed to find a derivative at some point on it, now you could just plug that point, x, plug the 1 in for x, plug the 2 in for y, and you have your derivative. Everybody got this? Okay. Here's some examples. So here's number. Ugh, I don't want to do that one. It's really ugly. Oh well, we'll do it. Let's see how we're doing on time. Oh, we are good. Okay, cool. So remember, anytime you take the derivative of y, it's y prime. And that's the thing you're looking for, right? Like, if you didn't get y prime when you did that, like, you wouldn't be able to solve for y prime. So that should be something in the back of your mind as you're doing this. So this says, find dy dx by implicit differentiation. This is number 8. And it's telling you to find dy dy dx. And by the way, that's what y prime is. It would be much easier if you write y prime instead of dy dx.
Yes.
Right? Okay. And so, here's the thing. Here's the object. 2x cubed. Give myself some room here. 2x cubed plus x squared y minus xy cubed equals 2.
Yeah.
Okay, so I'm going to take the derivative with respect to x of both sides. Okay, so in symbols here, d dx, I'm going to take the derivative with respect to x, both sides. This side's easy.
0, 0.
0. We'll come back to him. So now I'm taking the derivative with respect to x of this thing. What do I get?
6x squared.
6x squared. That thing.
2x times y prime.
Y. Product rule?
2x y.
Oh yeah, times y.
Plus y prime times x squared.
Plus, yeah, leave the first thing alone, take the derivative of the second thing. We don't know what y is, so we'll just use that symbol to show that that's what its derivative would be.
Yeah.
Minus, careful, because you have a product, you're going to need to do this, right? Because the product's going to turn into two things. So, how do I do this? Take the derivative of the first thing.
So 1.
Y cubed.
Leave the second thing alone. Add that 2, leave the first thing alone.
Times 3y.
3y
No,
squared times
Times y prime.
y
Yeah.
prime, right? Because you can think about it like this. If this were your setup and you said take the derivative with respect to that, you'd say, okay, take the derivative of the first thing, leave the second thing alone. Add that 2, leave the first thing alone, take the derivative of the second thing. 2 drops down, this goes down to 1, multiply by the derivative of whatever's in there. Yeah?
Yeah.
You gotta do that. And that's why you're gonna have a whole bunch of these to get in the habit of this. So there we go, okay? Now let's get this x squared plus 2xy plus x squared y prime minus y cubed minus 3xy squared y prime. 3xy squared y prime equals 0. What do I do? What am I looking for?
Y prime.
Y prime. So let's get the y primes by themselves.
So you can
I'm going to move
Add
it
that,
this way.
and then subtract.
And so what's left over here? 6x squared plus 2xy minus y cubed. This guy came over. 3xy squared y prime minus x squared y prime. I could factor out a y prime, leaving me all this stuff, which I'm not going to bother to write, because I know what I'm going to do with it in just a second. In fact, I think every single one of these that you do is going to be like that, where there's only one y prime left over. Now you take that, bring him downstairs. What was left over? 3xy squared
minus x
minus x squared. And then if you had a problem, like what is this at 7 comma 5, you'd plug in a 7 for x, you plug in a 5 for y, and you'd have your answer. Now, one thing I have not assigned homework on is they would then say, like, some of the questions say find the second derivative, find y double prime. Now that you have y prime, you just do it again, and every time you take the derivative of the y, a y prime pops out. And it's a pain, and who cares? So, I mean...
The quotient rule of that.
whole
Oh yeah, exactly, right? I mean, it would get really ugly. Although, I think the ones that they give you, they don't get that ugly. It's just a couple of them.
Every
And
time
I
there's a
didn't
y
bother.
there, there's another one of those huge things.
Like, the one they do in the book, and you could see just how crazy it gets. They give you a thing, and you end up finding that y prime is equal to negative x cubed over y cubed. And then they say take the next derivative. And so it's not as bad. but it's still a pain. And it's not, once you've done it for this, you get the idea.
Yeah.
Every time you take the derivative of y, a y prime pops out, etc., etc., etc. So, okay, that's how you deal with this. Let's do another example here. I want to do one where we actually find a thing. Ugh. Yeah, I guess we're going to do it. This is number 26, and it says, use implicit differentiation to find the equation of the tangent line at a given point. So this is 26. And this is a hyperbola. It's x squared plus 2xy minus y squared. Oops. Minus y squared plus x equals 2. And we want tan line at 1, 2. Okay, so what do I need to do?
The same thing.
Same thing, right? I'm taking the derivative of both sides. So I take the derivative of this side, take the derivative with respect to x. I could do this with respect to y. I could treat x as or y as a function of x or x as a function of y, and everything would work out just fine. But we're just gonna take a y as a function of x. Okay, so take the derivative with respect to x of this side. What do I get here?
2x
2x.
Plus.
Okay. 2 times some stuff. Now, we take the derivative of a product. What do we get?
1
1
times
times
y
y.
y.
Plus xy prime.
X, y prime. Good.
Yeah.
Now, what about this? This is minus
2y times y prime.
2y times the derivative of the inside stuff, which is y prime.
Plus 1.
Plus 1 equals derivative of 2.
0.
Okay, I'm gonna go ahead and distribute this 2 into here. I want to save myself some room, so the 2 comes in here. Yeah, everybody buy that? You with that? Let's make that 2 a little bit closer. Okay, so everybody that has the primes, we can leave them on that side. Everybody who doesn't have a prime, let's get them on this side. So we have a, it's all going to be minus. So minus 2x is gone, minus 2y is gone, minus 1. And what's left over is the 2x y prime minus 2y y prime. Did I do that right?
Wait, yeah.
Oh, you.
2x,
Yeah.
2y minus 1,
Yeah.
2xy prime minus 2y. Okay, okay, cool. Now, factor out my y prime. What's going on over here is this. What's left over here is going to come down here, so I'm not going to bother to write it. It would be a 2x minus 2y. Okay. Okay, so we took the derivative. Now we want the tangent line at a point of this thing. And this thing, I don't know, it looks like this. Right? We have some kind of crazy thing, and we want to know, okay, right here, what's the tangent line? Plug in a 1, get out a 2, and I want this tangent line. So what form does the tangent line have?
Y equals mx.
Y equals x plus b.
So plug in a 1 and a 2 for x equals.
So to find m, I'm going to plug in a 1 and a 2 to get it. So m is going to be what I get whenever I see an x, I plug in a 1. Wherever I see a y, I plug in a 2. They're both positive, so 1, 2, 1, 2. Okay, so that's negative 2 minus 4 minus 1 over 2 minus 4. So that's negative 7 over negative 2.
Positive.
So positive 7 halves. So y equals 7 halves x plus b. And now, what do I need to do?
Plug in 1 and a 2.
Plug in a 1 for x and we get out a 2 for y because this line has to touch the same point on this curve. And so I plug in, yeah, I'll do this over here. We have 7/2. I plug in a 1 plus b, and I get out a 2, like that. And so I have 2 equals 7/2 plus b. How about 2 minus 7/2 equals b? 2 is 4/2.
-3.
Minus 7/2 equals b. So b is -3/2. And finally, I get that the equation of the tangent line at that point is that guy right there. Everybody got that? Yeah. Okay. There's some cool stuff in here. You're gonna have to do a little bit of graphing. Just a little bit. It's just like, it says just graph this so you can see it. And I would suggest, like, especially when you have ones like this, where they give you something like this, and they say find the tangent line at this point, just go graph it. Graph this thing on Desmos.
I usually do that.
And yeah, I mean, it'll really help to reinforce this. Then graph that, and make sure that the two graphs touch at 1, 2. 1, 2. And it'll really help to reinforce all this stuff. Yeah, then you got a tough one. That's pretty tough.
41.
Leave 41. Yeah, 41. Oh, we got time. Okay, so I do, now that we have time, I do want to do one of the ones where it says find y double prime by implicit differentiation. And so let's do that with one of these. Let's do it. Alright, everybody got this? Okay, and now remember the workflow for finding a tangent line. You're looking for an m, you're looking for a b. To find your m, you got to get an actual value out of your derivative, which means you have to plug in a number into your derivative and get out an actual number, like we did with 7/2, right? Usually that's always the case. Very rarely is that not the case with tangent lines. You're always looking for some definite number for your m. Okay. Last but not least, here's 33. Find y double prime. So,
But we can solve for one.
you could, but it actually says find y double prime by implicit differentiation, and I'm willing to bet you it's going to be much easier to do it by implicit differentiation. The time that you waste getting your y, and then look, whenever you have a y squared, you end up with like a plus or minus square root something, which taking the derivative of that, then you got to take another derivative of that. Probably going to take you some time. And this, though, may or may not. We'll see. So, okay. First, let's find y prime. What do I do? First off, what is this thing? You should know what this is.
No, an ellipse.
It's an ellipse. Yeah, we divide by 9, right? And you'd have x squared, so no stretching in the x direction. That would be over 9 is over 3 squared, so it would be stretched in the y direction up to positive and minus 3. So it's this thing. 1, 3. Yeah, okay. Anyway, who cares? Okay, so derivative of both sides with respect to x d dx. What's that?
X plus 2y
Times y prime, which is the thing that you need. It had better show up. If it doesn't show up when you're doing this, you're doing something wrong. Derivative of 9 is 0. Okay, so now what?
subtract 2y, or subtract 18x and divide by 2.
Y prime is equal to
Negative.
negative 9x over y. Now, let's take the derivative with respect to x. Is that a quotient?
Yes.
That's a quotient. Okay. So, let me rewrite this up here so we got some more room. This is chill out, you guys. Please try to keep it down. Huh? Huh? Well, right? I mean, like, and here, I use brackets. I usually use brackets for operators. So, -9 times x over y. That might make your life a little bit easier, right? I mean, you could just treat that as your numerator, but you have 9s showing up everywhere, and blah. Let's just do it right here. And we'll multiply by -9 at the end. So, we take the derivative of a quotient, and what do we get?
So it's x prime times
Right, so the derivative of x with respect to x, which is 1 times
y
y
minus
minus
x times y
x times y prime
over y squared.
all over y squared. Okay, now, technically we're done, but the problem is, now if I said evaluate the second derivative at the point 1 comma 2, so what we're gonna do,
Plug in.
you can plug it right back in.
Oh, that's
And so we're gonna say, okay, that's the same thing as -9 times y minus x
this would be very
times
giant one.
-9x over y squared. Now you have everybody in terms of x and y. And so sometimes makes your life a billion times easier to do this. Sometimes it's actually better to get y by itself as a function of x. Depends on the context, but this is a very important thing to know how to do. And yeah, if there are no questions, I think we're good to go.
We have a minute to spare.
A minute to spare? That never happens.